Here we go. We are recording. Okay. All right. So let's put that here. Okay. So we've got a table which gives you powers of 2 for negative powers, right? And if you look at the first two entries, you see that you've got 0.5 and 0.25. So for number 1C, 0.75, this is 0.5 plus 0.25. Okay, I can do it in another way, but this is for free, right? If you just spot it right from the table right there. So you've got 0.5 plus 0.25. So that means that it's 2 to the power negative 1 plus 2 to the power negative 2, right? Which means that if you write that in binary, this is 0.11, right? So that's your answer right there. For 0.75 decimal is 0.11 binary, okay? So otherwise, how would I do it? So there's a single algorithm that will work for all possibilities. So let's take a look at, okay, let's just do 0.75, what the hell? Oops, sorry. So 0.75, if I multiply by 2, right? Because it's a fractional part, you multiply by 2. So this is 1.5, right? And so then you get rid of the integer part. So we've got 0.5, you multiply by 2. So this is 1.0, and this is your stop sign, right? Right there, okay? So you've got your first one right there, and you've got your second one right there. So 0.11, same thing. Okay, so that's the algorithm that'll work for any fractional part. So if I look at 1D, for instance, let's take a look at 1D. Okay, so it says that's a tougher problem in the sense that this is an example that I put in there so that you'd see that if you have, could you explain the floating point of the 9-bit mini float? Yeah, I will do that. I'll get there. Yeah. So you have, yeah, what was I saying? So you have 0.32 in decimal, right? So that's a terminating fraction. But if you convert it to binary, it might not terminate. So I said stop at 12 bits after the point. You see that this thing, it might not terminate, or it might be very, very long in binary. So I'll just start it just to illustrate the method. So 0.32 times 2, this is 0.64, right? And then I repeat, 0.64 times 2, that'll be 1.28, right? And then I take the fractional part, 0.28 times 2, that's 0.54. And then I repeat, and you keep on going like that, and you see that this could be very long, right? Yep. 54, that's 108, 1.08. Fractional part, 0.08 times 2. So you see 0.16. And this will repeat, right? Unless I made a mistake, but I think it looks okay. 0.16.
Yeah, 128 times 2 is 56.
Ah, damn. All right, thanks. Yeah, okay. So yeah. That's why it doesn't actually repeat. Okay, let's do that again. 256, that's right. Yeah. Wait, 0.28 times 2. Yeah, 56, thanks. 0.56. So 0.56 times 2, that's 112, right? So that's 1.12. That's 0.12 times 2.24. Fractional part 0.24 times 2.48. This is painful, eh? 0.48 times 2, 96, 0.96, and then 0.96 times 2, 1.92. Fractional part is 0.92. Okay, you see this is going to be like really long, and it's probably not going to stop very soon. 92, that's
184.
Yes. 1.84 and so 0.84. So what I need to reach is a fractional part of 0, right? So you see this is okay. You can probably guess you're not going to see one like that on the test, right? And if you do get in some kind of loop like this, or just like this really long thing on the test, you think, okay, I messed up somewhere. Okay, so I'll just stop here. Okay, so it means that you look now at these bits right here. So you're looking at 0.0101000011 and something after that. Okay, so that's how it works. Okay. If you have any questions, anything, just go ahead, eh? How about another one? Convert to decimal. These are a little easier. Okay, here's one. So converting to decimal. Okay, I've got, so this is number 2A. I've got 3, 7 in hex, right? So, oh, Josh, you have a question. Sorry, I just saw it. Yeah. No, gone. Ah, did I just throw you out? No. All right, no hands. Okay. So again, if you're in hex, these are hex digits, right? So the 7 here corresponds to 16 power 0, so that's units. This one corresponds to 16 power 1, so this is 3 times 16 power 1 plus 7 times 16 power 0. So that's 48 plus 7, which is 55. So that should be 55 decimal. Okay. Hopefully. I'm just going to double check the answer. I have them here. Number 2, yes, good. Okay. Okay, just another one. Number 2D. I have to convert to decimal 1101.10011 binary, right? So what is that? This is 2 power 4 plus 2 power 3. Nope, sorry. 2 power 3 plus 2 power 2 plus 2 power 0 plus 2 power negative 1, 2, 3, 4, and 5, minus 4, and minus 5, right? So this is 8 plus 4 plus 1 plus 0.5, and then I can look up the table 2 power negative 4 is 0.0625. And 2 power negative 5 is 0.03125. So I would just add those up and get what I want. In this case, this is, let me just cheat so I don't have to add it up. 2D, this is 13.59375 decimal. Okay, so that's also that's the straightforward, just reading off what the bits mean, right? Okay. Hopefully you know or will know soon what BCD codes are. This is right. This is pretty straightforward.
I get 14.1562.
You do?
Well, it doesn't really matter there, but
It should be 13 though, because
8 plus 4 plus 1 is 13. And then you just add up the decimals.
can you guys see what I'm writing?
Yeah.
Okay, good.
Because I don't know, did you actually like add up like 2 like tenths decimal and added a 1?
Was?
Because he probably no, because he probably did like 0.5 plus 0.6 or something like that, and then he actually carried over a 1.
Yeah, but there shouldn't be any carries, right?
yeah,
Because
you're right.
Yeah.
You're right.
yeah, it's
Yeah.
0.06.
Yeah, I didn't see it.
Yeah.
My bad.
Yeah. It happens. Okay, BCD is very easy, right? So number 4, we're asked what number in decimal does the following 4-bit BCD sequence encode? So I'm given 0110, 0111, 1001, 0111. So all you have to do is remember binary coded digit means each digit is coded in binary individually. So this is 7 in binary, right? This is 9 in binary. This is 7, and this is 5, right? So 5797 should be the right answer. Hopefully. 6, not 5. Gee whiz. Sorry. That's a 6.
So just to be sure, on the exam, we're allowed to use a table, right?
Yeah, the table we will be given.
Oh, okay.
ASCII table, powers, whatever you need.
Binary table.
Yeah.
Okay.
Well, yeah. we won't talk about the elephant in the room. We just won't talk about it. Yes. Where was I? Okay, these are the answers. Should I do? Okay, let's just move on to what seems to bother you most, mantisas and exponents and all that. And then if you want me to do some more problems on arithmetic and ASCII code, just tell me, okay? All right, so let's, okay, wait, but just one, okay, I'm gonna do number 10 here. Number 10, we're asked to encode minus 321 on 32 bits using the IEEE. So integer, this is important. This is an integer using the IEEE standard. Okay, so again, you have to remember there are 2 ways to keep numbers in memory. There's, for integers, there's a way, and floating point is another. These are 2 completely different ways of doing it. And here it's understood we're treating minus 321 as an integer, okay? So how do you do that? You have to, so it's the 2's complement, right, of 321 in binary, right? Okay, so I have to write 321 in binary, compute the 2's complement on 32 bits, right? Remember that the 2's complement is dependent on the number of digits or bits that you're using, right? It won't be the same thing on 12 bits or 8 bits, right? Okay, so 321 in binary, that's the first thing that I need. 321 in binary. The first way you can do it is the way I've shown you, is successive divisions by 2, right? That's the way we've seen how to do it. There is another way. So if you know your powers of 2, so 2 power 0 is 1, 2 power 1 is 2, 2 power 2 is 2, 2 power 3 is 8, 2 power 4 is 16, 2 power 5 is 32, 2 power 6 is 64, 2 power
You
7.
wrote down 2 to the power of 2 is 4.
Ah,
You
yes. Yeah. Thanks. 4, 64, 128, 2 power 8 is 256, and I won't need anything after that for 321. So another way of doing it, if you don't like successive divisions by 2, is to simply subtract the biggest power of 2 that you can, okay? So here's an alternative method to write it. So 321, I look at the biggest power of 2 that fits, that's 256. All right, so I'll subtract that. So that's 65. Is that correct? Yes, okay. I repeat, so I look at 65, what's the biggest power of 2 that I can fit in here? It's 64. I subtract, and I get 1. And I'm done, okay? So what I've found is that 321 is 256 plus 64 plus 1, right? So that's the game. You want to write it as a sum of powers of 2. So this is 2 to the power 8. This is 2 to the power 6, and this is 2 to the power 0, right? So 321 in binary is 8, 7, 6, whoops, 6, 5, 4, 3, 2, 1. I lost the
Supposed to be many zeros in there?
Sorry?
Is there supposed to be like 5 zeros?
I think so, yeah. So 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. Yes. So this is 321 in binary. Okay. Now, that's the first part. You could do it by successive divisions by 2 again, but here it was a little faster to do it this way. So now I need to find the 2's complement of this, but on 32 bits. So here's what I need to do. Okay, so what I need to do is to rewrite that on 32 bits. So now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'm gonna run out of room. 31, 32. Okay, so this is 321 written in binary on 32 bits. Now I compute the 2's complement of this. So you just flip all the bits and add 1.
Wait, but for the Mantissa, don't you need to pad it to the right, not the left?
I'm not talking about mantisses right now. This is not floating point. This is integer. Different. Totally different. right? So there are two ways to encode numbers. There's floating point and there's integer. Integer is just straightforward binary and 2's complement if it's a negative on 32 bits. If
Oh,
I'm doing
okay.
it, if I'm doing floating point, it's a completely different way, and I'm getting there right after. Okay.
Yeah, no. I just
Wait,
missed
so
the
for
problem.
so for integer, do you always have to do the 2's complement?
If it's negative, yes.
Okay.
Okay. Plus 1. So this is the answer. Okay. So yes. Okay, these are all ones. So this would be, so this is the contents of the registry, 32-bit registry. With minus 31. Okay. This is it. Okay. So don't expect 32-bit problems too much on the, what we'll try to keep it smaller. Okay. I mean, it could happen. You could get problems on 32 bits, but let me just check that I got.
Sir,
Yeah.
so you basically did the 2 complement at the beginning and at the end as well?
Nope. So I computed 321 in binary. So this is 321 in binary. This is this thing. Okay. What is the
Right.
2's complement? You flip the bits and you add 1. So I flipped the bits and I added 1.
Oh, okay.
That's
Yeah.
only when it's a negative, whenever you do the 2's
Yes.
complement. But the adding one, you always do it, right? Or no?
Yes. Yeah,
Okay,
absolutely.
yeah, that one you always do it.
Yep.
So for any like actual numbers, not a negative but a positive, all you would do is write the number in binary,
And
pad
that's
it
it.
to the left all the way
Yep.
with zeros,
Yep.
and then just add a 1.
No, you don't add 1. Adding 1 is part of the computation of the
Okay,
2's
for the 2's
complement.
complement. Okay,
Yes,
yeah,
yes.
I literally can't believe.
Yep.
It's so confusing.
Yeah.
Because whenever you do, like, example, you have the integer and then you have your floating points.
Yeah.
Like, which one is which again?
Yeah. Yeah. Okay, so let's do a floating point then.
That's the one I literally didn't do because I don't understand whatsoever.
Okay. Let's find one. Okay, I'll do number 11 here. Okay, so number 11. So number 11 is encode using the IEEE 754 standard for floating point. The number 47.5. This is in decimal. Okay. All right. So let's do that one. So the steps are as follows. You need to write this in binary. That's the first thing. Okay. So must write in binary. And not only in binary, you have to write it in normalized exponential form in binary. Okay, that's the key thing. Okay, in binary, not in decimal. Okay, so let's write 47.5 in binary. So there's the integer part and there's the fractional part. These are done separately, right? So you do 47 in binary. So what is that? Let's do it quickly. You can do it by successive divisions by 2 if you wish, but I'm going to do it by just removing highest powers of 2. It's a little bit easier for me to do it that way. So 47 minus 32, that's the biggest power of 2 that'll go in 47. I'm left with 15. Biggest power of 2 that goes in here is 8. That leaves 7. Then 4, that leaves 3, and 2, and that leaves 1. Okay, I did it very quickly, but basically what you see is that 47 is equal to 32 plus 8 plus 4 plus 2 plus 1. Can we check that? Yes, that's 47, right? So this is in binary, this will be 1. This is 2, 4, 8, 16, 32. Right? If I went too fast, just let me know.
Yeah,
Okay.
just the latter part, please. Like
Sorry.
from the, when you wrote 47 equals 32 plus 8. And then when you took that and wrote it in
Yeah,
binary.
okay. So this is 2 power 0, 2 power 1, 2 power 2, 2 power 3. 0, 1, 2, 3. There's no 2 power 4, that's 16. And there's a 2 power 5, which is 32. Is that okay?
Okay, yeah,
Yeah?
it makes sense now.
Okay.
Thank you.
Yeah. Yeah, so the intermediate step, if you want, is 2 power 5 plus 2 power 3 plus 2 power 2 plus 2 power 1 plus 2 power 0.
So basically the powers that you don't use, you
It's a
just
0,
write
right?
as 0.
Yeah,
Okay.
that's yeah. Okay. Okay, so I've got 47 in binary. The fractional part, 0.5, is easy, right? So we're very fortunate. It's not like 0.32 that we had earlier. That would be a mess, right? But 0.5 in binary, that's 1/2, right? You'd have a table available, but it's 2 power negative 1. So that's just 0.1 binary, right? Right, 2 power negative 1. Okay. So 47.5. So the result of this is that 47.5 is 101111.1 in binary. Okay, so that's the first step. Now I want to write that in normalized exponential form. This is absolutely critical. If you don't do that, nothing will work, okay? So now I need to have this in normalized exponential form. Okay. So what is that? It's scientific notation, right? But in binary. So this is 1.011111, and I've moved it 1, 2, 3. Oops, 1, 2, 3, 4, 5. Right? So times 2 power 5. Is everybody okay with that?
Yes.
Yeah, good. Okay, so this is the same number, but now it's written in normalized exponential form. So there's only one bit to the left, not one non-zero bit to the left of the point. So this is really where everything is going to come from to write it in memory. Okay, so now 32-bit floating point. Okay, so here's how, so there's the first bit. It's the sign bit. So the leftmost bit is the sign bit. It's 0 if it's positive, and it's 1 if it's negative, the number. So this is 0, right? Positive. Okay, then you have 8 bits for the, what we call the characteristic.
Sorry to interrupt, sir.
Yep, go ahead.
So you said the sign bit, if it's positive, is 0. So in this case, it's 0 because there's a 1 before the decimal point. Is that?
No, 47.5 is, there's no, it's not minus 47.5.
Ah, okay, okay.
There's
Thank
always going to be a 1. It will all, unless the number is 0, okay, which you won't get. If the number is non-zero, it has to have a non-zero bit somewhere. So when you write it in exponential form, it'll always be 1 point something times 2 to some power. Always, always, always,
Okay.
always.
Okay,
Okay.
thank you.
But it could be plus or minus. So this would be, so the sign bit will be 1 if you have a negative. So if the number were minus minus 47.5, sign bit would be 1. Okay, so negative sign bit is 1. Okay. So this is the characteristic, and this is what we call the mantissa. Okay, this is 8 bits. And this is the remaining bits, so that's 23 bits. Okay, I'll do it also for the so-called mini float after. It's the same principle, but with less bits, okay? All right, so how does this work? Let's start with the mantissa, which is the easiest thing. Okay, so what's the mantissa? What you do is you take all the bits which are after the point and you just put them over here, right? So that will be 0, 1, 1, 1. There's how many? 5 of them. That's 5 of them. And what do you put after? Zeros, right? It's a fraction. So you fill the whole thing with zeros after. Right? If you put zeros at the end of a fraction, you don't change anything. Does that make sense?
Is it the part where that's padding to the right?
Yes.
Or-
That's your. Right? So you need to put, the bit has to have some value. So you put zeros. It's a fraction, right? A 0.5, think in decimal, 0.5 or 0.50000, that's the same thing, right? But if you were to pad on the left, you'd be messing up your result, right? 0.5 is not the same as 0.05 or 0.0005. You're making the number much smaller by doing that, right? So you pad to the right. Okay. All right, now the characteristic. Exponent, if you wish. Okay, so wait, let me go back here. So it's this times 2 power 5. Okay, so we've got, our number is this. So this is our exponent. Now I've got 8 bits. This is the so-called characteristic. So what's the characteristic? This is the exponent that you have plus 127. So that's a convention, okay? It's not, it doesn't, the reason why this is done is that for the circuitry, if you wish, it's easier to handle computations. You have to understand that, think of a computer that's handling like millions of these numbers, one after another, and just adding, multiplying, subtracting, it's just like going one after another, okay? So you have to make this as efficient as possible. So when you're doing these arithmetic operations, one of the things that you have to do is when you have two numbers, is to compare the exponents. And because we're using 2's complements for negatives, it becomes, it's harder to compare them. So what you do is you shift by 127, so it becomes easy to compare. That's the way it's done, okay?
So this is what has to do with single precision, double precision, or is something else?
No, that's something else. The precision is given by the mantissa, not by the exponent. Okay,
Okay.
that's a different thing. Yeah. So that's okay. So this is the way this is encoded. Okay, so the characteristic, those 8 bits, is the exponent that you found plus 127. Where does the 127 come from? It's because, okay, no, I don't. I can tell you, but I don't want to do it now. Okay, it's big. So on 8 bits, you can write numbers negative and positive basically from minus 127 to plus 127. That's where it comes from. Okay, but let's just take it for granted. On 8 bits, what we call the bias is 127. Okay, so now it means that our in for this problem, in our example, so I've got 127 plus 5. This is 132, right? You write that in binary. That's 128 plus 4. It's really easy, right? So this on 8 bits, I don't know why I'm drawing it again, but anyway. So this is what you should get in your characteristic field. Okay, I'm gonna cheat up here and look at my answer. I hope I got it right. Maybe not. Yes. Yeah, all good. Okay, so sign bit, 1 bit, 0, 1, depending if it's negative, the number is negative or positive. Then 8 bits for the exponent plus 127. If the exponent, okay, I should do an example. Okay.
Sir,
No. Yep. Go ahead.
sorry to interrupt.
No.
Could you just re-explain? I don't get it from, okay, the 127 plus 5, it's all right.
Mhm.
And then you wanted to write it in binary, and then I don't understand. This is 128 plus 4. From
Yeah,
that
I mean,
point on,
okay, it's just, I know my powers of 2 well. So I know 128 is a power of 2. So again, what I did is, again, you want to write down 132 in binary. The algorithm that will always work is successive divisions by 2, but that's a
Right.
bit long. So I know my powers of 2. So I know 128 is just close to 132, right? So 132, I subtract 128. I've got 4 left. So I've got that 132 is 128 plus 4.
Okay.
128 is 2 power 7, right? 5 is 32. 6, yes, plus 2 power 2, right? So this is here, and this is here. Okay.
Okay.
Sir, will
Thank
there
you.
be a time where your characteristic will not fit in? Well, will be shorter than the like allocated spot, like the amount of digits you could put.
I see. Yeah. So here's an example. Good. I like your question. That's a cool question.
Because would you
Yeah.
would you pad it or would you just
Yeah. Okay, so here's an example. Suppose that we have 1.01011 times 2 power 0. Okay, so the number I have to write in memory, I'm already giving it to you in normalized exponential form. Okay, so okay, let's put a minus, right? So the sign bit is 1, right? Because we have a negative number. Then I'll have my 8 bits for the characteristic. I'll just do this like that, and then I'll have the mantissa. What? Like that. Okay. So this is my mantissa. That's easy, right? You just take these bits here and you put them here. 0, 1, 0, 1, 1, and you fill with zeros. You pad. Okay, it's a fraction. You pad on the right. You can put zeros on the right always. Okay, now the characteristic. This is exponent plus 127. What's my exponent? It's 0. 0 plus 127, that's 127. So what's 127 in binary? Okay, so you can do it the long way. So you just, I mean, all ways are long, but I mean, think about it. 127 is 128 minus 1. Okay, if you want to save some time. So you use your, so 127 is 1 less than 128. 128 is 1, 0, 0, 0, 0. So 1 less than that will be 1, 1, 1, 1, 1, 1, 1. That's 127 in binary. Okay? So that's what I have to write here. Where do I pad? Left or right? That's 7 bits.
Would that be left?
Yes. Exactly.
Because that's an integer, so you wouldn't pad it to
Yes.
the right. That
Yes.
would make it bigger.
Good. Good. If you put the 0 on the right, you're going to multiply the number by 2. That's bad, right? So yes, exactly. So you put a 0 right here. Yes. Good. So this is what this number would look like in memory. So that was a really good question. Okay. Okay, so now that was on 32 bits. Let's see what happens on 9 bits. So why did they do it on 9 bits? This doesn't really exist out there in the, I don't think so, on any machine. It's for us to play with. It's smaller, right? So to practice. So mini float.
Is that mainly for us just to practice?
Yeah,
or
yeah.
like
So it's like, yeah, it's a.
So it's like
Yeah.
playing go-kart instead of freaking having a car.
That's exactly it. Yeah,
Okay.
I like that. Yeah, it's, exactly. So we've got 9 bits. So there's 1 bit, which is the sign bit. Same thing. Then the characteristic is 4 bits, and the mantissa is 4 bits. Okay. Now, how does it work for this? So this is the exponent plus the bias. What is the bias here? It is 7. On 4 bits, the logical thing is to add 7. Okay, so here's an example. Suppose that I'm given minus 1.0101 times 2 power 3. Okay.
So really quick question. What's the
Yep.
biggest number you could put? 9 bits? Or to well, no, like in exponential form. In exponential form, that would be what? That's what I'm trying to ask. Yeah, I know
Good question.
I know it's a stupid question, sir, but
No, it's
still.
not. It's a
It's
Wemworth
just
question.
yeah, that is what I'm trying to get at. I didn't understand whenever they asked me that. I'm like,
Well, think about it, right? So you want to make this as big as possible, right? So the mantissa is maximum 4 bits. So you're okay. So in exponential form, this will be 1.84 bits times 2 power some exponent. Well, if you want to make it bigger, you're not going to make it negative. You're going to make it positive, right? And then, I mean, how do you make this as big as possible? I'm not going to tell you that you should know, right? It's
yeah, but I mean,
Yeah.
like without the exponent, the maximum would be 4 bits on the like on the exponential form, like
Yeah.
where you put ABCD. Yeah.
I mean,
For a second, I was confused when they ever asked me that. I'm like, that makes. I mean,
oh.
it's just whenever you're like on a 9-bit, you're like, because you would account for the sign bit and the 4 bits. For
Yeah, but again, it's. I mean, I think the question in the WebWorks is what's the biggest number you can encode in minifloat, right? So basically, you have to see what's the biggest number that I can write in exponential form with 4 bits after the point, right? So ABCD, you have to choose 4 bits to make it as big as possible. I mean, I think you can figure that one out.
Yeah, I mean,
Yeah. And so what's the exponent? The biggest you can make this, you have to be able to fit it on 4 bits and while adding 7,
Okay.
right? So just,
So I mean, you could technically go backwards from there.
yeah.
Okay.
Okay.
It's just
So-
the question on the WebWorks was like really tricky for no reason.
Okay.
It was like,
All right. Well, good luck. Sorry. You'll do it. You'll be okay. Where was I? Okay, yeah, minus 0.0101 times 2 power 3. So I want to write that in mini float. So this will be my mantissa, right? So let's do that. Sign bit will be 1. Then exponent. Yeah, of course. Okay, the mantissa, you just write down here, nice and easy. This is exponent plus 7. The exponent is 3. So this is 10. And what's 10 in binary? This is, yeah, so this is 10 in decimal, right? So if you write it in binary, it's 8 plus 2. This is it. So 1, 0, 1, 0.
Sir, it's not -7. Like
No.
3 minus 7.
No. No, the bias is plus. You when you write in the field, you add 7. You shift everything up. But if you're reading it to get the real exponent, you'll have to subtract, right?
Okay.
That's might be what you're thinking about.
And can it give you the decimal number? Not a decimal, but a negative number?
Sorry?
Like, if, for example, it's 3 minus 7, can it give you like a negative number? Yeah.
Well, if the I'm going to do one with a negative exponent, okay?
Okay,
But no, you can't get a negative. No, okay. So the only numbers you can write in this form, the exponent has to be between -6 and 7. It's impossible. So when you add the bias, you're always going to get something which is at least 2. 1.
So wait, the exponent has to be bigger than what the bias could. Like,
Yes, it
bias
has.
could be.
Yeah. Exactly. You cannot. Once you bias, you can't get a negative. It's impossible.
So the example of your bias right now is 7. It can't be a bigger, like not bigger, but like
Yeah. The
more
exponent can't be
negative
-8.
number. Yeah, exactly.
The exponent
And it
cannot be
can't be
-8.
could it be higher than 7? Yeah, no,
Nope.
no.
Nope.
Okay,
It won't fit.
it won't fit. Okay.
Yeah.
So it has to be between your 6, so -6 and 7.
Yeah. So you'd get an overflow if a machine was using mini float. Okay. So here's let's say I have 1.1011 times 2 power -8. Let's say this is the number you want to put in memory. In mini float,
That's gonna have to be in 32 bits.
you're gonna get overflow. Yeah.
That would have to be in 32 bits, though.
Yeah, you
If
need
you would try to-
yes, exactly.
You need more
On
you need more
32 bits,
data.
there's no problem. You can write that.
Okay,
no
but
problem.
why though the -6 and not like negative? Your bias cannot be a 0. I mean, add up to a 0.
No, if you look at the slides, there's a convention. There's a couple of values that are not used, but it's a pure convention. Don't worry about that. It's just,
I mean, technically it would be possible. But
Yeah,
you're not-
sure,
You
you
don't
could.
do it.
yeah.
Okay.
It's not, yeah.
So technically, with the convention, it's -6 and not -7.
Yep.
Okay.
Okay. Anything else? Do you want me to do another one or something else or whatever?
Can you do one with a mini bit mini float with bit given? Like you need to represent it in decimal value.
Ah, okay, the other way around. Okay, I
Yeah.
see. That's a little harder. Wait, I'll need to make one up. Okay, let's try one. Okay, so I have 9 bits. 1, 2, 2, 2, 2, 2, 2, 2. I've got this. Okay, so this is what the register contains, and I want to know, so what is the value in memory? This is mini float. Okay, so first I read the sign bit. It is 0. So I have a positive number. Okay. I look at the last 4 bits. This is my mantissa. So I know I have 1.0010, and I have to figure out my exponent. Okay. And now I look at the characteristic here, 1101. This is 13 in binary, right? And so I remove 7 and I get 6. So my real exponent is 6. Okay. You see what I'm doing? Yeah. Okay. So the number that I'm encoding is 1.001, well, 0 times 2 power 6. This is the number that was encoded, which is the same as this number. Okay, which happens to be, if I want it in decimal, that's 72. I think. I just made this one up, okay? But I think this is okay. Yeah, that's 7.
Will you be putting the notes for these up later on Leia? As in what we're doing in class right now, will you be putting this up for viewing?
Yeah.
on
So it's
Leia?
being recorded, and I'll post what I wrote up.
All right.
Yeah, I'll put them there. Yes. Yeah. Okay.
Your
Any?
notes are really helpful, sir, because sometimes we take notes, but we often forget to. Some
Yeah.
details.
Sure. Of course.
When we read yours, it's very
Yep.
precise. Thank you.
Any other questions or things I can do or?
Yeah, I have one.
Yep.
It's about single precision, double precision. Just could you like explain
But
the
that's-
concept basically?
But that's not. I didn't cover that, right? I can talk to you about later
But
separately.
it's the floating point web work though.
Is it?
Yeah, like there's one number that says the IEEE single precision floating point number given below in decimal and then you have to give it the equivalent in decimal. No, not in decimal. Anyway, yeah,
Can
it's
you
problem
which-
14. Of
Number
the floating
14?
point. Yeah.
Okay, I'll go take a look. But I don't think you need to know. I mean, single precision, double precision just depends. It's the number of bits which are used. Basically, that's all it is. But I don't remember seeing. Let me just go and check that.
So basically, single precision is 32-bit.
Yep, and then 64 bits would be double precision. But let me
Okay.
just check.
Now I'm so confused about about single precision and double precision.
You shouldn't be. It's not on. It's not material that you're. We didn't cover that. We don't. You don't need to know that. So, don't worry about that. Wait. Oh man. WebWorks. WebWorks. What are you? Question 14. Yeah, I mean, you can, number 14 or number 13, you can take the words single precision and remove them. And it's not going to change the question.
So it's basically just like
It's,
as you've
yeah. It's
explained
just, yeah.
previous
That,
problem.
you can just strike it out
Okay.
completely. It makes no difference. Yeah. Don't let that confuse you. Just remove it. So number 13, 14, the single precision there, just erase that. Okay.
Sir,
Yep.
the exercises that you gave, that you posted on Leia, will the test look like pretty much those exercises?
So WebWorks, exercises from the book, extra practice for test 1. If you look at all of that, that's, if you can do all of those, you should ace the test.
Okay.
Yep. Other questions? Or did somebody ask me a question and no. There was the single precision double, but that you forget about that. Other something else? No. Okay. So if that's it, you can when you have questions, we can Zoom even during the weekend if necessary. I'd rather not, but if don't worry about it, the test is on Monday, so So if you have questions, just send me a message, and we can meet in Zoom, and just don't worry about it.
Well, I
And-
do have a question.
Yeah.
Not about anything there specifically, but how much is the exam worth again?
It's 15%.
15%. Okay.
Yeah. And it's 1 hour plus 15 minutes, right? So you download the PDF, you answer on paper. Ideally, you print out the questionnaire and you answer on it, and then you can scan that, send it back in. That's the best for me. In PDF, not in some wild, weird format, not in JPEG. That's a mess. PDF. And
So we have to do it by hand.
well, you
Prefer.
if you can type it up, that's even better. But I don't see how that would be efficient. But if you want to type it, I don't mind.
Okay.
Sir,
Yep.
I noticed on YouTube that you also teach calculus and
Yep.
the course alike. I was wondering, currently I'm in the computer science tech program.
Mm-hmm.
And what if I would like in the future to transition towards the computer
Yeah.
science and math?
You should talk to people at the registrar's office.
Okay, so I would basically take some math courses during summer.
I
Okay,
I
okay, I'll ask.
suppose, but yeah, they're the people.
All
They're
right.
the right people to ask.
Okay.
I know the stuff that you would learn, but not the stuff
Okay.
to So yeah. Anything else? Okay, so I'll stop things here, and don't forget the WebWorks. Obviously, if you need extra time for the test, you must tell me. I have only one person up to now who has told me there was. I know I had a conversation with somebody in a Zoom meeting last week or this week, but I can't. I need you to send me a message if that's okay. All right, so I'm going to stop the meeting, post the video and the notes, and
You talked to me, and yeah, I'm still waiting for the answer
okay,
from
Doug, good.
Dina. I
All
sent Dina
right.
a message today.
Yeah, okay. So, okay, I'm gonna write it down here. Good. Okay. Yeah, student services, I think, is overloaded, but anyway, so that's fine. So I have your name. That's good. Okay. All right. Okay. See you guys. Good luck. And,
Thank you, sir.
If you have questions, just send me a message.
Have a good day, sir.
Bye.
Thank you.
All right.
Have a good day, sir.
See you.